basically say they are your most, the PCT is your most active reabsorbers. Reabsorption is to take something out of the filtrate, put it in the blood. Now, cells that do this work, well, the evidence is in the cell. Compared to the DCT, the PCTs, they're a little bit bigger. Their cell size is a little smaller. They have a brushed border in the lumen. Brushed border right here for absorption. Because the filtrate's in the center, you try to take things out of it as it flows through you. So there's a microfilari brushed border, and there's a lot more mitochondria to do reabsorption. So that's the evidence that they're your most active reabsorbers. They have microvilli, they have a brushed border, and they have increased numbers of mitochondria. So you know there's a lot of pumping going on across the cell membranes for reabsorption. So reabsorption, just to describe it using an analogy, they call this the fairy analogy. If you're trying to get a substance, say for example glucose, from one place to another, in this case from the filtrate to the blood, glucose needs a carrier. So the carrier, if there's enough carriers to carry this glucose, you can get 100% to the blood, as long as not too much is filtered. And so there's a rate of transport that you can take the glucose to the blood and say that's the concentration or the rate of filtration. Okay, and there's not too much glucose, you're euglycemic, there's plenty of transport time to get all the glucose to the blood so that nothing is excreted. If your blood glucose is too high, in this example down here, the term you want to know is this maximum rate of transport is called saturation. Well, there's just not enough transporters to take it, all the glucose in time. So some kind of slips past and you're going to excrete it in the urine. You have sweet urine. Normally glucose should be 100% reabsorbed. And so what you learn here is that glucose was small enough to make it through the filtration membrane, and all of it made it through. So one thing you learned is that the function of filtration by the glomerulus has no limits, okay? There's no maximum limit. Filtration, I'll put in parentheses, it's at the glomerulus. That was a quiz question here this morning for you guys. Has no max limit. What we see here for the process of reabsorption, there's a limit. You could saturate it, and then some could end up in the urine. And that holds true not only for reabsorption, but also for secretion. So the rule is reabsorption / secretion have max limits. I mean, this is an analogy. I mean, there's not stuff floating across. It's an analogy. Really, these are just membrane-embedded proteins. They're pumps, and they're carriers, and they're working. And they can only work so fast. They do have max limits. So let's move on. So the reality is for the cell in the PCT, this kind of holds true for any part of the nephron. If you're going to move something from the filtrate to the blood into a capillary, whether it be peritubular or vasorecta, you have to move it through this membrane and that membrane. Of course, there are proper names. The name of the cell membrane that faces the filtrate is the luminal membrane. because the lumen is the space for the filtrate to flow. Side opposite is basolateral. And you also have the interstitium and the capillary endothelium to get across, but we're going to focus mainly on these two membranes. That's where all the cell work is done for the process of reabsorption by the PCT, which is the main thing I want you to know. And so I think it's good to focus on the reabsorption of sodium. Keep in mind that these are your most active reabsorbers. Everything is reabsorbed. Things like sodium, glucose, vitamins, bicarb, just to name a few off the top of my head. Everything that the body wants to conserve is reabsorbed. But I think it's good for a student just to focus on one thing so you don't get overwhelmed. Reabsorption of sodium. So the cell physiology. Yeah, sure, go ahead.
For the sodium, they have the DCT have the sensor. Does the glucose and vitamin, they have in the DCT too when there's low and high?
Yeah, for those molecules, I don't think DCT has it. It's just for sodium as far as I know. Yeah. Okay, I have this figure here. Just put some numbers to sodium. Sodium. The kidney receives 25,000 millimolar sodium daily. Okay, that's how much it's filtering. The question is, well, that 25,000 is your 100% right there, right? PCT. At the end of the PCT, 33% is left, so you reabsorb a lot of it. Okay, pay attention there. You go through the rest of the nephron. By the time you get to DCT, there's only 5% left. By the time you get down here, there's only 0.4% remaining. So the nephron does a pretty effective job at reabsorbing almost 100% of sodium. Most of it is reabsorbed in this first part, the PCT, and that's what we're talking about. So you have pictures in your book like this one, and we've studied this before. In endocrine, where I taught the cell here, and there's filtrate, and there's blood, and it's the same lesson here. Okay, so you have a Pct cell, that does all the work. These are just plain old cells, epithelial cells, and they have a lot of function. There's a side that faces the filtrate. That's the luminal membrane. And the side that faces the paratubular capillary or vasorecta, depending on what you're talking about. It's called the blood over here. The blood capillary. This is the side opposite, that's the basolateral. Membrane. Okay, well, we're talking about the reabsorption of sodium. So first consider the numbers. That number in the middle in the cell, the intracellular, if you could measure the voltage, is negative 70. Okay, if you measure well, we learned about membrane potential in 430. But anyways, that's a negative number. Consider the electronegativity in the filtrate. Book said something like -3. And over here, outside the cell, is 0. All right, pretend you're positively charged sodium ion. You carry a full positive charge, and you look inside this place, and you see that it's more negative. If you're positive, wouldn't you be attracted to a place that's more negative?
Yes.
The answer is yes. So that kind of favors diffusion in the cell, this gradient. Also consider the concentration gradient. 15, I'll put my numbers off the thing. 145. 145. Okay, the concentration gradient also favors diffusion into the cell, where it's like high to low. Okay, so that's why on the figure I say, to get through this membrane on this side, the luminal membrane, is downhill, quote unquote. You follow your gradient, right? You just follow what's called the electrochemical gradient. However, consider the other membrane. Well, pretend you get in the cell by whatever mechanism. I'll show you how next. So you're in the cell now. And now the goal is to get across this other membrane, the basolateral membrane. You're positive, and it's less positive outside. You're positive, but you're moving against your concentration gradient. So you would need to expend ATP to get across this membrane, because you're kind of going uphill. You're going against the gradients. Uphill, going against gradients. So that's why I put this slide together for you. Because that is the goal. You got to get across this membrane and this membrane as well. This side you're going to have to burn some ATP. This side you don't have to. Now, what I'm going to talk about next is already on this figure. Solid red arrows on this figure mean, you can look in your book, primary active transport. Dotted red arrows mean secondary active transport. Processes that we talked about in 430. And so these protein channels and pumps, they execute those functions. And the direction the arrow pointing is telling you the direction molecules are moving across the cell membrane. So, take you through it, but the key thing to understand is, how do cells make this environment not only negative, but also low sodium? Okay, you want to create this negative 70-15 so that you favor sodium to move across this membrane to get into the cell. So that's the key for the student to understand the physiology of the cell.
Professor?
Yeah.
The 145-15 and 145, that's the amount of sodium?
Yeah, that's the sodium concentration.
How come it's 145 here, then it goes through and then it's 145 again on the other side?
Yeah, let's talk about that. The question is, it's 15 here, why is it more out there? Is that your question?
Yeah.
Okay. Well, let's look. Look at all this information you have to know. Oh, so where do you start? Number 1. Do you see the number 1?
Yes.
That molecule right there. Study that. That'll be in the answer to the question. Okay, that molecule, yeah, you studied it, so you already know it. What's it moving? That's sodium, and that's potassium. 3 out, 2 in. They move in opposite directions. That's the sodium-potassium ATPase pump. We do talk about it when we teach resting membrane potential. That's why I said you already know it, air quotes. Right? It was a long time ago. So let's remind ourselves what it does. Okay, I'm going to erase this. I need room to show all those. So the first thing to look at for sodium reabsorption is pay attention to the basolateral membrane. There's a sodium-potassium ATPase pump. potassium. And for those of you, I know it's early, and how am I expected to remember something I learned a year ago or something, right? Well, for those of you who do remember, or don't remember, the basic idea is it's a pump. So I always teach students that whenever that word is used, you're expending ATP, and there's an enzyme that breaks it down. So you burn ATP. So this is the function of primary active transport. You're pumping against the gradient. Primary active transport. So you pump out sodium, okay? You have to, because you're moving it against the gradient. And so by pumping sodium out, that's why the concentration of sodium was so high outside. You're pumping it out. And what do you exchange? You exchange potassium. Potassium is also a positively charged molecule, but look what potassium does. When you exchange it and it gets in the cell, it goes right back out. So not only are you pumping out positive sodium, the positive potassium is leaking right back out. So all that positively charged ions leaving is creating a very negative intracellular environment. Okay. So you pump out sodium, and then the potassium that leaks in leaks out. Basically what I'm saying is, well, that makes the cell, the intracellular environment, very negative. So I'll say that creates negative intracellular environment. Basically, negative 70 with respect to the outside, okay? And that's the same resting membrane potential as the neuron, okay? Also by pumping out sodium, put a little star here. Also by pumping out sodium, you achieve low intracellular sodium. I put a number to it, 15. Okay, give it a 15 millimolar. So we did all that hard work, the primary active transport, to create negative environment, low sodium. So that way, the secondary active transporter on the other side can allow sodium in. So on the luminal membrane, the function will be by this molecule. Call this, it's a sodium co-transporter. You transport sodium and you co-transport something with it. Co-transport means two things go across the cell membrane in the same direction. This is not a co-transporter, the other one. I'll be like an antiport, because the sodium and potassium are moving in opposite directions. But not the case here. You co-transport two things in the same direction. So for the luminal membrane, pay attention to a sodium co-transporter. Now it's kind of incomplete just to call it a sodium co-transporter. What are you co-transporting with it? It could be a variety of things. Anything that the cell wants to reabsorb, like glucose, amino acids, ions, vitamins, whatever it is. For example, let's say it's glucose. Then you would call it a sodium glucose co-transporter. And basically now this molecule is a secondary active transporter. Secondary active transporter. just to remind you, secondary active transport, you don't expend ATP. You do not. The primary pump does. But this one depends on it, because the gradient established by the primary one, the second one uses, right? Because you've already established negative intracellular environment, low sodium. The gradient is such that sodium is just downhill, right? You have downhill entry of sodium, and you take something with it along for the ride. So that's what I'm writing. Downhill entry of sodium. For example, take glucose with it. It gets a piggyback ride. It's like a wave of sodium entering the cell, and other molecules get to go with it, free of charge. Meaning, let me ask you this question. Is glucose going with its gradient? Yes or no? Doesn't matter. Well, it's going with the gradient. It's going against the gradient. Doesn't matter. It's getting in. The energy of sodium takes it in. Okay? I always think of like when I go to the beach and I see seaweed and kelp on the beach. And I think, was the seaweed following its concentration gradient? No, it's just the energy of the waves washing it on shore. Right? Same thing here. There's all the sodium rushing in, and this transporter can fit another molecule, and it goes with it. If it's a vitamin and this is not for vitamins, it won't fit. Okay, the molecule won't fit. It'll just keep on going. So that's how reabsorption occurs in the PCT. These molecules here. You take sodium, and a lot of things come along for the ride. Another thing to note. Took me years to see this. See this little thing right there? Boom. Right there, and then right there. Those are tight junctions. I want you to note the tight junctions. You ever have like a six-pack? You know, like the plastic rings that hold your six-pack together? Imagine turning that on the side. So that those plastic rings hold all the cans together very nicely, don't they? These tight junctions do the same thing for the PCT cells. So it makes it difficult for things just to slip through the net, because we want most of the reabsorption to be active control of the cell, not just leaking through like a leaky roof. Okay. So tight junctions are very good. So I'm just writing tight junctions to prevent leaking. I'm going to move away from this slide unless there's any questions. You can follow the steps there. There's other information on there. I got the main point I want you to get across, the uphill, downhill thing. Okay, well, there's other ways we can kind of talk about reabsorption, in particular using glucose as an example. There's some data analysis slides that are typically presented to students in physiology books. And what we've said so far is that, I think this is already in your notes, you're transporting something, for example, glucose, at a certain rate. So pay attention to units. Milligrams per minute. You're moving it a certain amount of mgs per minute into the blood. Yeah, but you can max out, right? Reabsorption, secretion, they have maximum limits. Filtration does not. So these processes depend on a finite number of pumps and carriers, right? For examples like the ones we talked about, this pump and this carrier. These processes depend on these pumps and carriers, and when they reach their transport capacity, you know, they've reached saturation. Okay, they have transport maximums, and so the data slides I can help you see this is shown here. So what they do is they plot the plasma concentration on the x-axis against the transport rate of the substrate in mgs per minute on the y-axis. So this is the rate you're moving it, mgs per minute, and this is the plasma concentration in mgs per mil. So pay attention to the units and you'll avoid some confusion. So I'm still talking about reabsorption. So if it's a plasma concentration, I'll use my concentration brackets for plasma. It's some kind of like milligrams for some unit of volume. It's a blood concentration. You pay attention to blood concentration of something because it may be filtered. And if it's filtered, if it's reabsorbed, there's a transport rate. If it's secretion or reabsorption, these rates have maximum limits. So the units will be mgs per unit time. It's a common point of confusion, so I want to make sure that that's clear. And well, anyways, when you reach your max, your transport max, TM, right? It's called saturation. And on this example, when something maxes out, it no longer increases. So 4, that's the rate of saturation in this example. You can continue to increase the plasma concentration, but once you reach saturation, you're not going to increase the ability to reabsorb it. Renal threshold is the plasma concentration at which saturation occurs. Renal threshold. The plasma concentration at which saturation occurs. You can read it right off the graph. The place where it first flatlines is 4 mgs per mil. In this example, let's look at another example shown here. We have different graphs at different locations of the nephron. And we're using plasma glucose as an example. And so let's look at the first rule. Filtration has no max limit. And how do you see that in this graph? It never tops off, right? Just keep going up. If it's filtered, it's all filtered. Okay, if it's small enough to make it through that filtration membrane, it'll be filtered. No matter the concentration, even if it's 500, you just filter all of it. Okay, so filtration has no maximum limit. This here, they give you a normal range of glucose. Okay, this is reabsorption, say for example, at the PCT. So to kind of give you a visual of what's going on here. Here's a glomerulus. It's all red. There's no gas exchange. I'm not talking about that here really, but okay, the afferent arteriole here, efferent arteriole here, blood coming out, blood coming in. And let's say glucose is coming in. We draw 3 little green balls to symbolize glucose let's say the plasma concentration is within the normal range. Let's say it's a 100 mg per deciliter. 100 mils is a deciliter. So let's start off at 100 mg per deciliter. And let's say it all gets filtered. Let's remember the structure we're talking about. It's going to be filtered in the Bowman's capsule here. I'll just draw the nephron simply like this. Simple tube. And let's say it's all filtered, all three of those little things. Let's say my three little green balls represent 100 mg per deciliter. Not very much. And it flows by the PCT, and there's cells that can do the reabsorption. And here's a paratubular capillary or something. And you're operating within sub-max range, so you can reabsorb all of it. You got 100% reabsorption in this first example, which means you excrete 0, okay? Because you're operating sub-max. Let's keep going in this example. Let's go to 200. So let's double it. So I'll draw 3 more little green balls. And it all gets filtered. You're still sub-max, so you're going to be able to reabsorb all of it, and you excrete 0, and you just keep going. Let's go to 300. 300, that's the max, 300, but that's the first time you reach max. So 300. I'll draw 3 more green balls in here. I'll draw 3 more green balls here. And I'll draw 3 more green balls here. And they're all reabsorbed. You still have 0 excretion. But when you finally exceed your max, let's say, I don't know, just go to 400. You're going to start excreting now. 400 mg per deciliter. Maybe you drink a 6-pack of Pepsi. It's too much sugar. It's still all filtered because there's no limit for that. But however, this is the first point where you cannot reabsorb at all. You'll finally start to excrete glucose in your urine. So that's kind of like when you look at the third graph. Collecting duct, excretion. I mean, prior 1 to 100 is nothing because you reabsorb it all, but you first start to excrete at 300, okay? That's like standing on the verge of excretion. And that's how you read the last graph. Okay, is there any questions on boom, boom, or boom, those three? If you overlap them, it kind of makes sense, right? Dotted line, the red dotted line, you just keep filtering, okay? And it's kind of, you start excreting if it gets too high because the rate of transport maxed out. So to summarize, when the blood concentration, for example, of glucose is so high, when it's filtered by the glomerulus, all of it cannot be reabsorbed. You just exceeded saturation. The amount, quote unquote, left over or not reabsorbed is then excreted. You have sweet urine. The high blood plasma concentration at which a filtered substance begins to spill into the urine is the renal threshold. Let me ask you this question. So what's the renal threshold in our example? 300 is correct. Very good. What's the TM? Well, it's right here. Can you read that? 375 mg per minute. D is correct there. What's being used up when saturation occurs? In these choices, what do you think makes the most sense? You know, mistakenly, a lot of students say glucose. Glucose isn't being used up. You got too much glucose. The transporters are. Yeah, think about that. All right, next topic. It's kind of a side topic. This is acid-base balance. And this is kind of some of the figures come from a different chapter in the kidney, but it kind of fits here because we're talking about kidney cells. And we study these kinds of figures too, so it kind of fits. It's a different topic. So in this unit, whenever we talk about acid-base balance, it's of the blood. That's understood. Blood. Okay, so even if I don't say it in a question, balance what? Blood. Okay, that's kind of easy to remember. And let's remember the normal range. The pH of blood should be blood plasma, 7.35, 7.45. You want to, that's the balance. Just keep it within the homeostatic range. And why the kidneys can help is you can actually reabsorb or excrete different things. For example, I say, are you reabsorbing bicarbonate? That's bicarbonate. Always remember that. That's our base. And the second thing I say, are you excreting protons? A proton is a hydrogen ion. That's our acid. Because a hydrogen atom is a one proton nucleus surrounded by one electron. So if you remove the electron, you have a proton. So sometimes I call them protons, sometimes they're just called hydrogen ions, but that's our acid. And you can excrete it. For example, if you did this, excrete, reabsorb. Oh, I'm sorry, got that wrong. Reabsorb, excrete. So by now you should know what those words mean. Get rid of the acid, put more base into the blood. What effect will that have on the pH of blood, do you think? If you accomplish both of these things? It should increase the pH if you have more base and less acid. Okay, you're having a chem prereq, that should be clear to you, I think. Well, so what? Well, this could be very helpful if you're trying to combat or counteract, compensate for acidosis. So that's what we're talking about here. Okay, there's different ways the cell can do this. And the main thing I teach is you can't excrete hydrogen ions. The molecule is too small. It just attacks biological tissues. So you have to glob it on to a buffer, a bigger molecule that can't be excreted. So that's what I want to teach you, know the different buffers. So one thing to know is that the base is reabsorbed quite a bit. Because the kidney will receive 4320 amount of base, call that your 100%. And then so you kind of reabsorb it along the way, so you have very little remaining. So cells are very good at reabsorbing base. That's the point of that slide. And move on from that and basically reabsorb base. What do you do with the acid? How do you how do you excrete it if you just literally can't excrete hydrogen ions? Okay, again, urine can be very acidic because you can acidify buffers within the kidney. So I want to teach you a few of them. Pay attention to where you are in the nephron. This says PCT. So these are PCT cells that can do this physiology. All right, so these are ammonia buffers in the PCT cells. Ammonia, well, you need an amino acid because ammonia is NH3. So glutamine, the amino acid glutamine is metabolized. This physiology depends on that being available. Glutamine metabolism. It enters the cell and you break it up into pieces. That's what metabolize means. Now pay attention to these words that they put. Deamination, oxidation, and particularly the last one, acidification. You acidify the amine group. So ammonia, you acidify ammonia. You just call it good old H3. When you acidify ammonia, you attach a hydrogen ion to it. Right? You stick it on there. Because you can excrete that, which is, well, you know, right, properly. That's an ammonium ion. That you can excrete. So if you look at the figure, you're on the one hand, you excrete the ammonium ion, and on the other hand, you're here, you reabsorb a new bicarbonate ion. So, you know, check the boxes. Excrete the acid, reabsorb the base. That'll help raise pH, okay, to combat the acidosis you may be experiencing for whatever reason. The cause of the acidosis, we'll talk about it later. But anyways, the kidneys can help, is the point. So that's what I want you to understand from the ammonia buffers. There are other buffers. For example, in the collecting duct cells, there's phosphate buffers. Well, here's an important thing. We saw it in respiratory, where you hydrate the CO2, right? It's like you combine water and CO2. Does anyone remember that enzyme? It's not California. CA. You guys remember that one? Carbonic. What's the A? Anhydrase. Here it comes again. We have our carbonic acid, which is a weak acid. So you have a hydrogen ion and a bicarb. You pump that out, okay? And you attach it to a monohydrogen phosphate. It becomes a dihydrogen phosphate, which you excrete. On the other end, you reabsorb the base. Acidify monohydrogen phosphate. So that's our, right? And then becomes a dihydrogen phosphate. H2PO4, full negative charge. Okay, so that's, you acidified it, boom, you excrete that molecule, and you reabsorb the base. So both of these, the ammonia and the phosphate buffer, is very effective at combating the acidosis, because you excrete the acid, reabsorb the base. There's a third buffer system. Bicarbonate itself is a buffer system. And that's shown here. Going back to Pct cells, they also do this. Another very busy figure to look at. They give you a 6-step process. And it usually makes sense to start with number 1. Actually, on this one, I think it makes sense to start with number 6. Pay attention to CO2. CO2 is an inert gas molecule. It's so small, it can diffuse right into a cell membrane without a carrier. Okay? So that's the first thing. CO2 diffuses into the cell. And then it goes through the same physiology we just talked about. You hydrate it with the water, you get your weak acid, your carbonic acid. You pump out a hydrogen proton, or a hydrogen ion, and then you get the base reabsorbed. Okay? Now this time, let me ask you this. Look at the hydrogen ion when it's pumped out. Look what happens to it. And look at the products down here. So here it is there. What happens to this hydrogen ion? Where does it end up? It ends up in the water, okay? So, and the thing is, you reabsorb most water. So technically, you're not excreting the hydrogen ion this time. Think of water as, well, it's not an acid, but think of it as an acid, because that's where you're hiding this proton, hidden proton. Water is mostly reabsorbed. So basically, you're not excreting it. Not excreted. Like you did in the buffers. Okay. But you are recovering bicarb. But it's not like it's not a new one. Because if you're not getting rid of the acid with it, it's kind of a wash. I guess you get some of your base back. Well, anyways, this last system isn't as effective in combating the acidosis because of the hidden proton being mostly reabsorbed. So it's something you probably will never notice unless I mention it is when you reabsorb the bicarb. Let me show you what's missing. Do you see how they put? It's hard to see if the light's on. You reabsorb it and they say new. Okay, it's new shiny toy. And here they put new. Here they put new. How come they don't put new here? It's for the reason I just stated. It's not new. When you put the water back with it and you're not getting rid of the proton, this is not new anymore. So it's a very, very subtle difference in the figure that I think you should be made aware of. But anyways, that's what I want you to know for the bicarbonate buffers. And there's another thing here I put. Bicarbonate is indirectly reabsorbed. What is meant by that? Let me answer my own question. Let me first let you look. Here's what you reabsorb here. here's the bicarb you recover. It's not directly reabsorbed, it's indirectly reabsorbed. And why did I say that? Let's go backwards. There it is there. Where is it before that? There. Or is it before that? Huh. Okay. Where did it come from? Oh, okay. So the reason why it's indirectly reabsorbed is you didn't take up bicarbonate. You took up what? CO2. You took up CO2, it became bicarb, and then you reabsorbed that, okay? So that's what's meant by indirect reabsorption. If it were direct reabsorption, you would take this molecule right here and stick it directly into the blood, but you don't do that. The cell doesn't do it that way. You take up the CO2 first. The other question I always ask here, students tend to forget this one. How does glutamine metabolism increase the pH? I simply put that one because students always forget that it's part of the ammonia buffer system. Just remember glutamine, amine, it's ammonia buffers. Okay. Well, anyways, the answer to the question is you excrete the acid at the same time you reabsorb the base. Okay. So now it's new because you have one more base and one less acid occurring at the same time. That's what makes it new. Okay, acid-base balance. We'll talk about it again. I just wanted to go to the cell physiology of that before moving on. Any questions on acid-base balance? Okay, loop of Henle, nephron loop. Let's talk about that. Because I did PCT, acid-base balance, so we're just going to move through the loop of Henle, DCT, collecting duct. Okay, finish off the nephron. The loop of Henle is next.
So, Professor?
Yes.
Can you go back to the previous slide, please? And you talked about, like, how does the glutamine, how does glutamine metabolize, increases pH? So it doesn't increase pH, right? Because it makes it more acidic, so it's decreasing pH instead of...
No, it does increase it. It makes it the blood more basic because you excrete the acid and reabsorb the base. That increases the pH. Say pH was 7.2.
Okay, it makes it more basic.
More basic.
Yes.
Yeah, increased pH. All right, loop of Henle. The kidney can help regulate blood milliosmolarity. Kidney can help regulate it at 300 milliosmolarity. You do this by pulling water and salt out of the filtrate. In other words, you reabsorb lots of salt and water. The loop of Henle, the LOH, it uses a countercurrent mechanism, that's the key there, to pull lots of water and salt from the filtrate. And when you do that, this dramatically varies the urine concentration. So you can maintain the blood plasma level at, well, the number is 300. Okay, so the terms used in the book, loop of Henle, LOH. Blood plasma concentration is 300 milliosmolar. Osmolarity is just molarity. Molarity is concentration. Osmolarity is biological concentration because the saltiness of the blood affects osmosis, osmolarity. And the number 300 may not mean anything to you. Let me see if I can put it in perspective. Plasma is almost like water. Okay, it's straw colored, but it's almost like water. It's very dilute. So think of this as a dilute number. It's like saline. Saline is 0.9% NaCl. So imagine a cylinder, we got a 100 ml beaker of pure water. You can just add 0.9 grams of sodium chloride to it. That's all it is. That's all this number is. Okay? So it's pretty dilute. And what you do is you pull water and salt out of it help concentrate urine so you don't lose all your fluids to the urine. And so the loops of Henle we're talking about are the ones with the juxtamedullary nephrons of juxtamedullary nephrons that concentrate the urine. What that means is urine output is less, and the concentration of the urine is, well, obviously increased. It's more yellow. So imagine this, you're forcing this 300 milliosmolar filtrate through this long loop into the medullary interstitium. What you need to know is that the medulla is very salty. Now, we got fresh kidneys for you today. Don't taste it. Okay, just trust me. There's a salt gradient there. Some people eat kidneys. I'm sure it tastes delicious, but not today. They're for dissecting, not consumption. So, cortex, 300. That's our, our normal plasma concentration. But there's this progressive salt gradient. So what this says here, the osmotic gradient, the osmolarity, the solute concentration of the medullary interstitial fluid progressively increases from 300 to 1200 to the deepest part of the medulla. Okay? The long nephron loops of juxtamedullary nephrons create the gradient. They act as a countercurrent multiplier. Let's write that. Keyword create. Here's one of my renal pyramid. It's like 300 in the cortex, and as you get progressively deeper, it goes, maybe it's 300 there, and it goes 600, 900, maybe at the tip, it's like 1200. It gets progressively saltier as that loop of Henle extends all the way down and goes all the way back up. And you're forcing filtrate to go down and all the way up. Okay? And so it creates this gradient. And students, that's the physiology we want you to know. They label this creation process a countercurrent multiplier. The LOH acts as a countercurrent multiplier. So what is that? Well, something's multiplied. Well, it's obvious right here. What times 300 is 1200? 4. You multiply it 4 times from top to bottom. That's the multiplication. So not only do we have to talk about the countercurrent multiplier, we also have to talk about the vasorectum. Because once you establish this gradient, the blood supply can't wash it out. You can't bring blood through here and remove all the salt. So you need a mechanism to kind of leave well enough alone. So I'll talk about the vasorectum next. Let's first talk about the loop of Henle and why it's a countercurrent multiplier. Your book handles it very well, I think. Okay? They tell you just barely what you need to know, because it's actually pretty confusing. I've read a lot of books over the years, and I just kind of roll my eyes because it's even confusing to me. But this I understand, and it's pretty clear what the author is trying to get across. It's the best way to present it to students. They give you 2 parts of the limb, the descending limb and the ascending limb, and you can pay attention to the thickness of the limb. There's a part of the descending limb that's thicker and then thinner. Talk about the thin descending limb. Okay, that's what I want to talk about. Consider thin descending limb. Because it's water permeable. The filtrate loses water on the way down. Water permeable. So water leaves. So what that's going to do is it's going to concentrate the filtrate, because if water is leaving and entering the interstitium as you flow down, by the time you get, X marks the spot, to the elbow, you're removing water, it's concentrating the filtrate. So that's why they changed the color of the filtrate to a darker yellow, darker brown color. At the elbow, you can assume you're equilibrating with the interstitium. So that having been said, what's the concentration here? 1200. Right? So I guess you could note that. Filtrate concentration. It's like 1200 milliosmolar at the elbow. X marks the spot, right? What elbow? My elbow? No, I'm talking about the bottom of the loop, the hairpin loop there. So the thing about being a loop is you go down, but then you go back up. So you make the U-turn, you go back up. And the thing to consider on the way up and out is the thick ascending limb. Sometimes books call it the TAL for short. Well, anyways, the thick ascending limb is watertight. It's water impermeable, but it has a lot of salt pumped in it. Water impermeable. However, there's these salt extruders, these sodium pumps. You're going to pump out salt, but you're not going to lose water. So on the way up and out, you're going to like pump out sodium. So think about this. If you pump out sodium, you don't lose water. You're diluting, you're re-diluting the filtrate. So you were at 1200 at the elbow, you could expect you'll be like 300 or 100 at the top. So 100 to 300 milliosmolar, depending. There's a range here. But the point is, you concentrate it and then you you remove salt. I'll be right back. I just got to change the battery here. Okay. Yeah. Well, anyways, where I left off is you dilute the filtrate. So how do you create this gradient from 300 to 1200? Understand this feedback mechanism. This is a positive feedback loop. Recap, on the way down, lose water. On the way up, lose salt. And this is a positive feedback mechanism where on the way down affects on the way up. Okay, so the loop, it says start here. I don't like to start there. It doesn't matter because we'll end up there. I like to start where we started, where the filtrate enters. I like to start here, where water leaves the descending limb. Let's start there. Think about this physiology. Water leaves descending limb. Okay, good. Water leaves. And so what do we say that do? You increase the saltiness of the filtrate. That's what I say. What they say is increase osmolarity of filtrate. Okay. Well, what we also said was you've got like a concentration of 1200 at the elbow. I'll kind of add that to mine. 1200 milliosmolarity at the elbow. Okay, then you kind of like go on the way out there. Just kind of match what they do and what they say. You've increased the osmolarity of the filtrate entering the ascending limb. So basically, to paraphrase that, you have more salt to pump out in the TAL. Remember, TAL is thick ascending limb. Anyways, that's kind of like my next point in the concept map. Well, so you have more salt to pump out, so you pump out salt. So therefore, by pumping out salt, you're increasing the saltiness of the interstitial, right, of the medulla. Well, if you're increasing the saltiness of the medulla, then more water will leave on the way down, because water will leave towards more salty. And this keeps going, the salt connecting, it keeps going. Okay? You just keep, you could go around as many times as you want. But that's the positive feedback. And this is the answer to how you create creates osmotic gradient from 300 to 1200 milliosmolar, and I will just kind of leave it at that. Any questions on the feedback loop? Yeah?
Why does it do that? Why is it needing to concentrate and then?
Yeah. Let's see. Well, you want to remove the water, right? Because by removing the water, you lose less fluids to the urine. Okay, that's the main thing. That's basically it. You remove the salt, so the water will come out. Okay? The goal here is concentrating urine. That's the goal. So when you remove the water, you've accomplished that goal.
Is more water going back in though as it comes up the loop?
No,
Oh, okay.
this is water impermeable.
Okay.
Yeah, that's that main point there. Okay, so it's very important to understand both. On the way down, you lose water. A question you might ask later after you think you thoroughly understand it is, well, if you lose water, don't you wash out the salt? You don't, because all the time on the way up, you're pumping out salt, so you create and maintain it. Okay? So it's very important both. So the whole point, concentrate urine. If you remove water, you can do that. Okay, any more questions?
I'm still
Yeah.
confused. So if we follow this loop
Yeah.
we did right now, so we say in the initial that water leaves the descending layer,
Yeah.
where the fat portion is of the descending layer. And then we increase the saltiness of the filtrate because water is leaving, then it's getting concentrated.
Yeah.
And then it becomes at the elbow, it is 1200.
Yeah.
And then we getting into the descending part of the loop.
Ascending?
Ascending.
Yes.
Ascending part of the loop.
Mhm.
And then there's more salt in it because we had 1200. So
Yeah.
that is going up, so it's still 1200 there.
Okay. Once you pump it out, it's not, but yes.
So, so since we have more, we are pumping out salt outside.
That's right.
And then when we go to the medulla, you're saying its saltiness, it increases the saltiness of the medulla.
That's
so
right.
We're pumping the salt out into the medulla?
Yes. Into the, area outside the loop,
Outside the loop. Oh. So then,
but in the medulla.
so if the medulla has a lot of salt,
Yes.
that's why the water is following the salt and it's
Yes.
building up?
That's why it leaves out. So that's why you need both, on the way down and on the way up. If you only did one, you wouldn't get the other, so,
Thank you.
yeah, no problem. Okay. Well, the other question we have to answer is, how do you supply blood to this salty medulla without washing away the salt? Because the blood is a fluid that can wash it away. And you do it by having the same arrangement. Have a capillary in the shape of a loop. So fluid can flow down and fluid can go up. So the loop of Henle creates the gradient, but the vasa recta, it just kind of leaves it alone. It just protects it and preserves it. Vasa recta protects the medullary gradient. The loop of Henle creates it. The vasa recta just protects it. Okay. You're able to supply blood to this gradient and you don't wash it away. So, let me ask you one question. Just look at the figure, look at the colors. Does gas exchange occur at this capillary? Yes, because it goes from red to blue. Great. But also pay attention to on the way down. On the way down, blood concentration is 300. And the blood is being put into this salt gradient. And what happens is, it's a capillary. So it's just going to make passive exchanges with the interstitial. Blood capillary makes passive exchanges. With the medulla. Look, on the way down, blood is flowing down, going down. Blood is entering a salty medium, so it's going to equilibrate. You equilibrate. So to equilibrate, salt enter, water leaves. Okay? To equilibrate. That's all you're doing. The blood is just equilibrating. So when you get to the elbow of this capillary, I mean, what's the blood concentration? It's 1200 and it's becoming deoxygenated. Okay, so now look, you usually don't have U-shaped capillaries, but in this case you do. So that means you go up. So going down, going up. As you go up, it becomes progressively less salty, and the blood just became very salty. So on the way up, you make passive exchanges. Salt leaves, water enters. So again, you dilute the blood. You re-dilute it. So that on the way out, the top number there is like 325. And then the number going in is 300. So the point of that is you don't remove salt. You don't wash it out. Imagine if this was a normal capillary where it's a straight tube. You go in and you go out. You would remove 1200. Okay? And that you would wash away the gradient. So the fact that you make a U-turn and go back up and out, you barely remove any salt, you protect the gradient. So I'm writing here, you don't remove much salt, because on the way up, salt leaves, you put it back. Okay, you take it and you put it back. So you're able to just kind of like make passive exchanges, you don't remove much salt, therefore you protect the gradient. Any questions on that? Vasa recta. The loop of Henle and the vasa recta, those structures that are together, but we teach them separately. So because I showed you different pictures, I don't want you to think they're in different locations. They're actually together. Let's take a break now. When we come back, I want to talk to you about your lab before you leave here. We're doing a simple sheep kidney dissection. And so the procedure is, well, you have to form your groups like you usually been doing. About 10 kidneys, so groups of 3 to 4 ought to do it, but what you got here is what you need per group. You just need one little half sheet, really. But what the half sheet has is 12 structures. 12 structures. So be sure you get 12 pins, 12 dissection pins. I'm going to pull your sheep kidneys out of the fridge. I'm glad I caught the lab tech when I went and changed my battery. We're changing to getting rid of the seals trays I put out. I'm putting them away. We're not using those anymore. It's too much work for you to wash them, right? Don't you like that? You don't wash them good enough, or it's a pain for you guys. We're using these disposable ones, okay? And then I use a little thing to catch the blood. And so you use these, and I'll have the kidneys out. You go over here. When you're done, keep the weight goes in the right bag. And I'll drag the glove bin. The tray and all your gloves will go in the red bin. What do you need to label? So first, you gotta cut your kidney, right? So you butter that. Just cut it. That's what you got, right? Just get some tape, maybe a lighter color, and just get a pen, and just make labels. Literally stick the pin with the label to the structure. I'll come right off the top. So we'll write it aloud and come back. How you doing? 15. There's a range. Yeah, thank you.